So welcome back, everybody. Second week of classes. We are, as I was mentioning earlier, the topic for this week is intermediate representations and their translation mechanisms. So we are pretty going to follow the flow of the compiler. In the last lecture, I introduced different phases, front end, and gave some reading material for you guys to pace through. So please try finishing those even at a high level, get understanding of the core ideas. Details may not be important, but finish reading those quickly. And then the next phase, which is really important here, is the intermediate representations. What are the different ones? What are the trade-offs? Understanding of those, and we are going to also have a translation mechanism, which is an important one from the AST representation to the triple or quad IR representation. So those are the two sets of slides which I have put under modules, and the first one deals with the intermediate representations, which we are going to get started about. And at the end of this, we'll try to do some homework to get ourselves familiarized with this topic, and then we'll get started on the next topic of analysis, control flow analysis, and we'll do further things at that particular point. We'll get into LLVM, etc. So as you can see in this next slide, we have really important phases of the compiler. This is a little bit more in detail than what we saw last week, which is front end and the middle end, which is now a new phase, which I inserted. The job of front end remains the same. Takes the source language and does all kinds of syntactic and semantic analysis on it, and produces the intermediate representation, whatever that may be, at the end of it, after the program is found to be legal in terms of its syntax and semantics. The middle end is where the lot of action happens, which is very interesting, which transforms an IR into another form sometimes that is closer to the machine. Starts with AST, which typically it gets converted into a different representation like quad that we had seen last time. Operand 1, operand 2, operator, and the destination, that kind of representation. And more importantly, it transforms it so that it is more efficient. It removes certain inefficiencies from it, reorganizes it, and so on. And then the backend again takes that particular IR and converts it into the target code. And the middle end usually consists of many interesting things which do translation, conversion, transformation, optimization, etc., etc. So that is what we'll first focus on in this class, the middle end, and then later towards the end we'll talk about some backend and machine-specific optimizations. So the IR design is really very, very important because the amount of information and the kind of information that you represent in the IR allows the compiler to undertake different types of analysis first, and that affects its precision in terms of what it can do, because sometimes some information is lost in the IR, as we'll see, and therefore the compiler is not able to do certain analysis, or it will spend overly huge amount of time in reassembling some information, and that time will be lost. Depending on how the IR is organized and its attributes, the speed of compilation is also critically affected. So not only the precision of what we can do and find out, but also the speed are important criterion in designing the IR. So some of these design decisions which are involved in choosing the kind of IR representation we have to deal with how fast we can generate it. Because if complicated IR and if we had to expend a lot of time in just generation of the IR, then I think the advantages, at least as far as the speed of compilation, will be compromised. Then the second one is how quickly we can manipulate it. It can go from one place in the IR to the next place where some change is to be done. That is also decided by the annotations and the attributions that you the IR. So for example, just when you do, this is an analogy here, when you use an editor, Emacs and so on, and when you navigate your source code, many times you go from a call site to the place where the function or a procedure is defined. And how fast you can do that, it really depends on your productivity of how well you can generate the code or write the software. So something similar here happens. The other three criterion, which are levels of abstractions, allow you to, as I said, do certain analysis and maybe prohibit certain other things. The freedom of expression, this is more has to do with especially different languages are compiled onto the same IR, as you know. That way we can leverage the same backend. And so what all we can express there, whether it captures the language's intents or not, or whether it loses it, those kinds of things. And then of course the size of IR, how big it is, because many algorithms which manipulate the IR, as I was mentioning, are order n square, n cube, in fact sometimes n fourth also. So if you have a too long an IR, then the compilation is going to get slowed down again because of the size. So these choices are made very carefully, and they also evolve over a period of time. And LLVM IR is one great example of a really well-designed IR, which has been learned. The experience came from a lot of different IRs, including GCC and so on. So, but without getting into too many specifics of a given IR, what we are going to do here is look at some classification, some high-level view of different IRs, the way they look, and what they allow and what they are typically used for. So you can see here that the parse trees which get generated, so these are sort of organized in some sense in terms of the control flow of the compiler phases. So as you know, after the parsing and so on, the parse trees are the type of IR that are produced. If you remove certain placeholders from the parse trees, such as the variables, not the tokens, but non-terminals, which are sort of used for expansion. If you get rid of those non-terminals, then you can see that the IR is AST. And that is typically used to keep the representation here, you can see, is very close to the way the sentences in the language or statements look like. And so this is typically used for source-to-source translation. Almost the information that is kept here is very similar to, or almost similar to, the source code, the array names, the indexing, for example, even the control flow, the keywords, they're all kept there. And the intent here is that you want to pretty much keep the information from the source language similar to in the IR, do certain analysis quickly on the IR, and maybe add some annotations and things like that, and do what is called as a source-to-source conversion. So where is this very useful? So take some, for example, a case here, like you're taking a C or C++ program, or a Fortran program, and you are doing some analysis for finding out if the loop is totally parallel or not. How it is done, we haven't seen that, but some analysis is possible on the array names and their indexing patterns and things like that. What is called as a dependence analysis, and through that, if we can declare a loop to be totally parallel, then we can insert here the pragma like an OMP, OpenMP, totally parallel loop pragma at the entrance of the loop, and then pass on the newly generated source code to the parallelizing compiler, which will try to split the loop and do certain further analysis of it. So this is an example in which we are pretty much keeping all the source program as is and doing some analysis on it. And that's why it is kept in the same form as closest to the source level, which is like an AST, and translated into with annotations and additions into another IR, another language. And so that's the reason why we use trees. And we'll talk a little bit more about that as we go further. The second IR is a linear IR, which is what we have been looking at, which is a quad or a triple IR. And here is where it is very suitable for translation into the machine code. So this happens further down in the compilation stage, wherein the intent is get rid of the source language abstractions like records and arrays and all kinds of different things, but to convert all of that into a form which is like a temporary, which holds the results of sub-expressions, where the indexing has been implemented, perhaps through a base plus offset, these kinds of things. And it is closer to the machine form of two operands and a destination with an operator. And this is the IR which is typically used in the most commonly used at the end of the front end. It is generated for the middle end typically, which I was talking about here. After the front end, this ASTs are converted into this type of an IR, which is a linear IR. It is manipulated typically as a part of the middle end, transformed, optimized, etc. And in that particular process, we also try to analyze certain properties of this IR in terms of its control flow, for example, and leads to what is called as a hybrid IR. So it is not just in terms of top-down flow, but it has certain transfer of control. So for example, we split this into a group of statements which are going to execute linearly, what we call as basic blocks. And we'll be talking about that extensively. And then from there, the control goes from one block to the other, and they execute. And using this representation, we know that after certain groups of statements, we could go from this particular point to that particular point in the IR in one or the two ways. And that will give us an idea of what is going on in terms of what are the different possible paths of execution, what are the different properties of those paths, and so on. So this is where the IR from linear is converted into hybrid, and that's one of the transformations. Further there, from the control flow standpoint, we could have even further sort of annotations on it, and we'll talk about those also. So for example, if you want to just focus on optimizing the loops, we'll capture a subspecial graph of control flow graph as in terms of the loops, and then we'll focus on only that region. So we'll put further annotations on the graph that is generated. We could also do a single entry, single exit kind of a region that may allow us to do certain optimizations, which means that the control flow can come in at the entrance of this region in one way and go out in only one way, and that has certain properties. So for these specific reasons, we'll try to do this conversion, and that will lead to a combination of not just a group of statements one after the other, but they will get grouped into regions, they will get grouped into blocks, there will be transfers of control or going from one region to the other, there will be loops which could get detected, etc., etc. So let's do some examples of these kinds of things and what they entail and so on. And here is starting with the AST. We have some example here in which more and more details of implementation, in short, not of abstraction. The abstraction goes at the higher level, but the implementation of that abstraction on a given platform, even an abstract platform, is revealed as we go down from one to IR to the other. So here is a simple reference, A of ij, and this is really important in AST representation. You can see here that A is an array, and I and j are two indices of those. And our goal may be goals may be different here at the higher level of an IR. One of the simple goals could be that we just want to make sure that this array is not going out of bounds in terms of their declaration and so on. And by doing certain analysis, making sure that I is within the limits and so is j, we'll be able to ascertain that. And that's why this representation is simple and is efficient at that particular level. However, if our goal is to actually implement this array, which is what the goal is in our middle end and downwards, then you can see that the IR could be converted into another form which looks like something like this. What is going on here is we are trying to do the address calculation. I won't get into the details of it. You can easily see it. It's basically address calculation code that is going on in terms of using j to index the array and then using I to further index and multiplying with the dimensionality of that particular I or j. And you can see that mainly the goal here is the address calculation using the value of j, subtracting 1, multiplying 10 by it, and so on, and then adding I to it, whatever is sort of the manipulation that is to be done. And finally, you can see that the value is loaded into R of A of ij, and that's basically calculates the dereferences this A of ij in terms of the intended purpose of implementing this A of ij operation. So in of IRs can be expanded depending on the purpose of this. And typically it is construed that the higher level IR is just a very closest to the source level, but some expansion from there can be done depending on the compiler stages and what they try to achieve and so on. For example, the same reference that we saw earlier, you can see here that is further expanded at the AST level, not necessarily by binding the implementation to specific registers or temporaries or any of these mechanisms, but just abstractly. So here we know that the array representation is kind of exposed now, which is doing j-1 first and then multiplying it by 10 to do the offset calculation. And then I think there's a typo here, which is I-1 is being done, and then multiplying by 10 and then adding j-1 to it at the top to get your offset calculations. The number of rows, each one of them multiplied by the dimensionality, that will get you the total elements over there. And then you add the offset in terms of j minus 1, and it will give you the array offset is basically how the we will try to do the A of ij kind of calculation, and that's exposed here. So we could have some transformations here. For example, if we decide to do bounds checking, or if we have to do certain parallelization, all these indices are exposed there, the dimensions are exposed, and so we might try to find out the effects of these at the high level. Let us look at a generalized AST and then see how it looks, which is what the first step in terms of translation is. So from the parse tree, we get rid of non-terminals, as I mentioned, and we want to keep certain simple references which are organized by the hierarchy of computation. So if we have something like x minus 2 times y, that is represented as AST over here, and could try and then do certain transformations of these to make them more efficient. Typically, associative transforms, commutative transforms are useful for reorganizing and balancing the trees in terms of their computation, in terms of the registers and so on. And some pre-processing like that is done. So Clang, for example, does some of these. If you look at the Clang's associative and commutative phases, it will do some tree balancing for even further helping out the code generation. But the other form, which is also there in certain compilers, is allows you to even do some sharing across the ASTs instead of replicating the expressions. For example, given these two expressions on the right-hand side, you can see that certain operands are common to both of these. Although there is no common sub-expression between the two, the operands are common. And so the representation can identify this explicitly by keeping track of which are the values which are referred to in an expression. So z equal to x minus 2 times y is represented, as you can see on the left-hand side, AST, and when it comes to the next expression, w is equal to x divided by 2, it is referring to, you can see the same operands x and 2, and that's why there are arrows from the node on the right-hand side to these two subnodes. So if there are any common sub-expressions here, for example, if the second one also had 2 times y as a common sub-expression, then you could see that one of the arrows would go straight to the star, which is the subtree over there. So what does it entail you? So as you go top down in terms of the ASTs and process them, and then you do lookups for the operands or sub-expressions, this will allow you to do certain optimizations. So for example, if you take this IR and identify something which is common, you would avoid maybe replicating the computation of that expression because the further code generation stages would simply say we'll generate 2 times y, use that result in both of these, if that were the case. Of course, in this particular example, not the case. It is just that there are shared operands here. And this also tells you certain things. It tells you in a very simple way the referencing frequencies of the operands, even though there is no common expression here or sub-expression. You can see that X is referred twice here on the right-hand side. That could be deduced by the incoming arrows quickly on a given operand. And that might help you to try to do something special for this operand, trying to keep it in the register and things like that. So this encodes, as you can see, different types of information, different levels of information. The effort that is expended in terms of gathering this information is very simple, because it is going from one statement to the other. Originally, as you can see, that the ASTs encode the information only within a statement, because it is pertinent to that statement. But across statement, you can keep some simple information inside a given block, for example. So for example, consider an if statement, and within the body of that statement, so many arithmetic statements. If you do this type of common operands gathering within that particular level, at least within that block, you have managed to catch some common sub-expressions or deduce the frequency of operands and things like that. And that's a small amount of work because it doesn't need any analysis, which is complicated. It is simply a matter of, as you will see, when you translate AST to its quad representation, you will be walking these trees, and you will be linking the trees in a simple way without undertaking any control flow or any such analysis. Of course, the scope of this information is small, and so it's its effect, and so is the effort. So, of course, as I was mentioning, the most useful thing that really happens is in the realm of taking the AST and then converting it into some kind of representation which is closer to the machine or implementation. So, of course, we have two types of commonly used machines, which is like stack-based machines or JVM type of a machine. And this IR would be walked in terms of x minus 2 times y. This tree could be walked here, and we could generate something like, first we had to evaluate 2 times y as an expression. So what we could do is generate something like first push multiply these 2 times y, and then push x, and then subtract this sub-expression from that. So you can see that the steps which are involved here start with the left-hand side operand push x, then go towards the right-hand side subtree to push 2, push y, then multiply that, generate the code for that, and then finally walk back and cover the negative sign there to convert it into subtract and so on. So this is pretty much post-order traversal of each subtree, and that's pretty much would generate this type of a code. And you can see that the names are in here. The stack keeps track of what is going on where, and you will see that that's pretty much what the stack machine is able to do. So you don't generate any more names or sub-expressions, and you don't give it some symbolic things in this particular case. However, the more common one, which is there for, of course, our hardware that we use, is of the form of 3-address code, as I mentioned, which is x is equal to y of z. First operand is y, second is z, operator is op, and then the destination is X. And typically at the level of converting the AST into these triples, we call these triples, or rather these IRs, which has three names. These three names are typically symbolic names. They are not real registers. Further processing occurs on them because we may or may not keep a name in a register, physical register. So we'll be just symbolic at this particular point. We'll emit a temporary name and things like that. Now, in terms of representation and conversion of this particular IR, what we'll do is another example. We'll break it down in terms of sub-expressions. So x minus 2 times y, for example, this type of thing, we'll be evaluating 2 times y to what is called as a temporary. So we'll allocate that, and then we'll be doing x minus that temporary, and then finally generating the z. So we are introducing here the temporary names and things like that. And this is where the second lecture is going to give a lot of details of how do we generate the temporaries, how do we walk the trees, how do we return the temporaries, how do we combine them, and how does the code generation takes place from the AST into the three named format. This is most important and commonly followed practice in compilers to generate this. The important thing to note here is there are three operands here, and the destination is very explicitly called out in terms of a temporary name. This is one representation which is commonly, for three address code, it is commonly adopted in terms of how it is kept. So sometimes we have things there which are explicit, which are holding the values. So for example, this multiplication here of R3 and R2, the result is held in R1. So this corresponds directly to certain instructions. There are load stores which do not have all three operands, which typically have only two operands. And their destination is operand is number 2, for example, as you can see in these cases. The destination operand is typically, depending on the instruction, for example, load will load it from Y and load it into R1, and then the store will store it from a particular register, and then do the necessary things as per the implied source and targets. So all the instructions need not have all three names, but many of them will have, and some of them will have only two. And again, this is a matter of holding the results explicitly. There are advantages of explicit names because, again, we are able to reuse the names. We are able to manipulate what to do with the results and so on by using the names, which may not be possible if each instruction has its unique destination. So this used to be the case, that each instruction is a unique destination, which is implied. It's not an explicit one. So this is implied that, for example, the first instruction has its target in a location 1. Whatever that 1 is abstract and is different from 2, it's different from 3, different from 4, and so on. So the targets are the same as the instruction number here. and they are of course distinct because they are all distinct for different instructions. And the reason for this not keeping an explicit target name was to save space, and therefore this was adopted in earlier types of compilers. Um, and that time the space was really a problem, but later on this was not the consideration anymore. And so the more common practice nowadays is to really manage the temporaries not implicitly but explicitly by giving a name. And one can think of the name itself as
Professor, we can't hear you any longer. If you can hear us.
Yeah, Nathan, I'm back. I'm going to pull back the slides again. I'm sorry, I don't know
Okay, good.
what happened.
So we can hear you again.
Yeah, what happened? I had to literally restart my machine and somehow it picked up the network again, although I'm sitting very close to it. So anyway, so let me just take a minute and get back the slides here. And just a minute. Can you see my slide now?
It's just blue for me. Yes, that's what chat says. So I see your mouse and I see a blue screen, but no slide.
Let me. Okay, how is it now?
Okay, yes, I can see that.
All right. It is snafus. Sorry, guys.
Yeah.
Let's get back again. So, so what I was, where we were at was some of these older representations, which we don't want to get into, is these triples and where the operands also were implicit, and that's how the space was really conserved for keeping the IR because that's really decided the size of programs that you could compile. But modern compilers all use explicit representation, and the speed of compilation is much more important than going through the indirect references, and that's what quad representation is what we'll be focusing on. The in these quad representation, as I was mentioning earlier, the main job that you have is to really generate these temporaries to hold the results, and the management of temporaries is an interesting issue, which you can see here that this simple example again, continuing that x is equal to z equal to x minus 2 times y. We have assigned a temporary for holding a value 2. Then we are doing the load on y, getting the value of y into 2. And then we are evaluating 2 times y by destroying the value of y that we already have here. You can see that that happens in step number 3. That is T2 times T1 is done, and we could have assigned here a new temporary, which is T3, or we could have tried to reuse T2, and we have chosen here to reuse T2. The main reason is this, that if there is use of this y in multiple places, maybe you don't want to destroy that, but just use this T2 and evaluate 2 times y into T3. So that's the decision which will be taken then. But in this example, and the absence of anything else. We are going to just use the load of y as an intermediate step, and that's why we are destroying it, and we are doing T2 times T1 here, holding it back into T2, and so on. And further down, we could again make a decision whether to destroy T2 or assign some T3. And you can see the big trade-off here is the intermediate results are available if you do not do any destruction. And sometimes they will allow you to do certain very interesting optimizations. For example, if you do not destroy T2 further down, then you have 2 times y available, and wherever 2 times y is there, you could reuse T2, saving certain operations, and this optimization is called as common sub-expression elimination. However, if you do not have, then it may not be needed. If you have a continuous evaluation of an expression and many expressions will not go across certain regions, then you want to kind of destroy it and reuse the temporary name. Regardless, you can see that these names are not really per se memory spaces, but abstract names. So finally, what will happen is some of them will get mostly folded into registers. The values will be simply, depending on the implementation of the underlying machine, will flow from register to register. So no real memory will get allocated for many of these names, introduced names in the stack. And that therefore, the code generation will eventually handle the size of the names. Finally, coming to the last part of it, the linear code that I have been talking about so far in terms of quads or triples being very, very less, is not used these days much in practice. The quads mainly, those linear code going from, as the program is translated from AST into the underlying linear code like quads, we still don't know what is going on in terms of control flow with that. And so we would, after this linear code is generated, we would try to organize it into further refined information or representation, which will give us a very clear picture of what is going on in terms of the analyzability of the code. So here is that representation, which is called as the hierarchical representation, and we'll be using this substantially throughout this class and also in the LLVM, IR, and so on. It is called as a control flow graph, which is a very standard important representation. And what we have here is a concept of basic blocks. What is a basic block? We'll come to many more details later, but it is about when the control executes linearly through the sequence of those operations, they're all supposed to be contained in a basic block. So in this case, we have A equal to 2, B equal to 5, executing one after the other in the left-hand side. Similarly, on the right-hand side, A equal to 3 and B equal to 4, and those are two basic blocks. Each one of the other ones is also a basic block. But you can see that across these blocks, the control may go from one place to the other, but not necessarily it goes all the time. So for example, after the if statement executes, depending on its outcome, we'll go either left or right and execute one of the two. But it will never be the case that we go and execute either the left always or the right always. It will really depend on the control flow. So that is why they are all in separate basic blocks. However, if we are within a basic block, after we execute A equal to 2, we are definitely going to execute B equal to 5 in the left-hand side. So that is the difference between the order of execution. In one case, it is may. In the other case, it is must. And there are implications of that because we can take this into account, we can do more analysis, we can try to infer a few things from them and optimize using this representation. So, to be able to incorporate this into the analysis, that either we go left or right, but never is the case that we do one of the two always. And maybe even some cases we do it, if we go left, we don't go right, and things like that. Such information, if it is used in the analysis, we can make it more precise, and we can take advantage of this when we try to organize the IR further, or optimize or transform it. And that's why this representation. How is this done? We'll take the linear IR and we'll do certain analysis on it and break it down in terms of the basic blocks. We'll also analyze what is going to happen across those basic blocks in terms of whether we can go from one place to the other, and we'll put an edge there and put that may relation everywhere we can. If we cannot, of course, then we'll not have an edge. So that way we'll maintain the precision of what is may not, but may-wise we'll lose the precision because we can go from one place to the other. It's not necessarily that we will go always, and in some cases we'll see the difference that we may not ever go in the dynamic sense of the execution. For example, if this predicates x is equal to y is never true for any values of x and y, because of certain reasons. Maybe x was evaluated to be y plus 1 before this. And because of this, x being equal to y plus 1, x is equal to y is never true. Then you can see that one of the branches will never ever execute for this particular program, regardless of input. And because of which we may not go on that particular edge. And that's obviously a source of imprecision because we have assumed that we can go. So further analysis will reveal us that certain edges may become what we call as unreachable. If you take one edge, we may not be able to go on the other edge. That is, certain paths could become unreachable and so on, inexecutable in runtime. And more precision through analysis, if we can build into using this representation, the more and more precise and better it will get. But to summarize, this is a representation of a hierarchical flow graph, because you can see that at the higher level we have just these blocks which go from one to the other. And at the next level of hierarchy, we have these statements or IR statements which are embedded in each one of those. And we can analyze the properties, staying just within a block, staying across a group of blocks, or going across the whole graph, and that will tell us different properties which we can leverage. So finally, this is where we arrive at what is called as the LLVM's IR, which is called as the static single assignment form. So what is really the difference between the IR that we just seen earlier as a quad IR and static single assignment form in terms of what it does? The big difference is this, that left-hand side, you can see that we have the IR statements. X is equal to something is the first statement, y is equal to something is the next statement. And then we have while x less than k is the third statement. Below that, we have x is equal to x plus 1 as another statement. So just focusing on x's, we are talking about different x's which prevail at different program points. You can see that at the top level, we are talking about some x which brings in a value from the top, goes across the second statement, and then feeds that value to the while loop the first time. But then the value is redefined inside the value inside the while loop. It generates another value, x is equal to x plus 1. So definitely a different x exists from this point onwards. So as x is reassigned, you can see that it entails different values. And that is something which is captured on the right hand side in the SSA form, as you can see. The first x is called as x0. And the second x, which is going to get redefined inside, is going to be x1. See that. And further down, if the x is incremented and yet another x is coming in, it will be called x2 and so on. So what it is showing is these different x's are given different names. So they will be all treated separately because of the names. You may say that, hey, suddenly some two x's can come together, and that very much can happen. So you can see here that there is something called as a phi function, which is combining two different values of x's, which could be coming in here. So for example, let me just go back to the previous example here, and let's consider this a here. A is equal to 2 is coming from left hand side to the lowest basic block here, and a is equal to 3 is coming from the right hand side. So we could have a is equal to 2 or a is equal to 3 prevalent at this particular point of what we call as join of these two edges. These two edges are joining here, and so that will be indicated as a1 phi a2. So it will be choosing it will either between a1 and a2, a1 being on the left hand side, a2 being on the right hand side, and we'll pick up one of the values and we'll feed it depending on the edge through which it comes. So this allows us to precisely tell us that which A's or combinations thereof exist at which program points, and allows us to then use these properties to decide on what to do with this X, what to do with these A's, for example. So if a equal to 2 and a is equal to 3 is coming at this point, you can see there are two different constants. So we are not going to be able to replace the bottom a by either 2 or 3 because if we do so, it will lead to bad illegal code. If we decided to replace a by 3, then if a equal to 2 comes in, it will be wrong, and vice versa. However, if both of them were the same value, a equal to 2, both sides, then we could easily replace this a by 2. And we don't have to consider any other a in this particular process because these are the only two a's which can come down at this particular point. So this allows us to do very fast analysis and fast navigation of the IR because we know precisely which values are participating where. How do you generate this particular form? Of course, we have to transform it from this quad IR into this particular form using the control flow graph and so on. And this is one of the things which we'll be again learning through the class. So we'll expend some time in conversion of the IR, but it will pay off because now we know that we have a very fast way of analyzing it. So to conclude, we have different levels of IRs present in our compiler world. Typically ASTs followed by quads, followed by hierarchical quads, followed by SSA. And we don't stop here. Many times we go further down and there are target specific IRs. Which will be pertinent to certain types of instructions in terms of what they do, what different operands they have, things like that. And we keep maybe the IR3, which is shown here, could be a backend specific IR, and that will be used in that backend in a particular way. And even within the backend, there could be different levels closer and closer to the assembly, which will be used for keeping certain properties and using those for optimizations. Now, one last point here is that using these IRs, of course, the final objective of these is to generate efficient code. And we have two models of code generation typically, and we have seen this probably in earlier classes. One of the assumptions could be that we got to keep all the values in a register and before we can operate on those. And that's basically a RISC type of a model. We must keep a value in a register and operate on it and things like that. And in order to bring the value into register, or when we cannot keep it, we have to use the load stores. The second model is more traditional, that all the values are to be kept in memory, and then we promote them to registers directly before they're used, and we insert the necessary load stores for bringing these values. And then obviously, because we insert so many load stores, right, before each of the value, we have to insert a load, things like that. There will be so many load stores which will be interspersed through the program, and then we'll have a problem of getting rid of redundant load stores. So for example, if y is referenced and then y is again referenced, we'll have two loads here. And then obviously the second one is unnecessary and we have to get rid of it. Whereas in the other model, we'll be just bringing the value of y in a register and continuously operate on it until we cannot keep it for the reasons of we are short of registers wherein we have to toss the value away or it is not safe to keep it in a register. That may be another reason. So I know I didn't pause, I mean, at least in an active way, but let's see if there are any questions on these. And I don't know how far we are in terms of time. We have about 5 minutes. At least we'll get started on the next set in case let's see if first we have any questions.
There's not anything in chat. I don't see any hands raised.
Okay. So let me now switch to the other set of slides. Can you see the new set of slides?
Yes, I can.
Okay. The IR code generation is the title of the slides. And so here is where we are going to see the conversion of the ASTs into the quad IR. And this is a step for converting, going from the front end into the middle end. So let us see what happens here. And this is some quick overview of what we did. So the main thing that occurs is we are trying to take this code, which is more at the source level in terms of AST, wherein the hierarchy of operations is established by the tree, and we are going to then translate this into a form which is closer to the machine of implementation. In an abstract sense, we are not, of course, generating specific instructions for the assembly instructions, etc., but we're capturing the format of those in terms of the different operations that are implemented on a given machine. So, for example, some of the common ways to do this is as follows. So all the arithmetic and logical operations we have are typically captured in terms of either 3 operands or 2 operands as shown over here. X is equal to Y OPZ, operated through z, and x is equal to y ops y. This one of them could be a load kind of operation. The second one could be, for example, a plus b type of operation. Then we also typically have data indexing, which is captured here, which is a way of trying to access the data by using offsets. So, for example, y offsetted with z is able to give us the data, and it's placed into x, or the reverse, x indexed by z is equal to y, which is storing the value in an array. And then we have simple operations which are moving from one register to the other, such as x is equal to y, things like that. The important thing here is capturing control flow through two types of branches. As you can easily see here, which are a very simple branch called goToX. Remember, this is a compiler intermediate form, so we are not doing goTo oriented programming here. But this is an unconditional branch which is going to transfer control straight into a particular place labeled as X. So there is something which is going on here, which is a label of a particular instruction. And this is going to be simply a jump to that particular label. Now the other one is what we call as a conditional control flow instruction, which is you can see that if YOPZ, if that operation's result is true, and the op operation here is a sort of a comparator, so like less than, greater than, equal to, not equal to, etc., or even logical expression, if there are logical operands here, like true, false. So if the result is true, then we are going to take a jump here to a label X. So that's a control flow conditional kind of operation. And then typically we support the function calls, and we'll have instructions such as pushing the parameters of the call on the stack. You have learned about these parameter passing and all these mechanisms in terms of how the functions are supported through the call stack. So first we push all the parameters, then we do a call to the function, which is shown as call foo here. Paramex is pushing all these parameters one by one. And at the end, then we have a return value, which the function is bringing back to the point of call. And that return value will be then stored into a variable, etc., as per one of the arithmetic expressions, instructions. So you can see here for this simple code, and we'll do the details of how this translation works in the next lecture, is however, what is going on here is x minus 2 times y is evaluated here by first evaluating 2 times y in the AST, and first by bringing 2 into temporary 1, y into T2, and then doing T3 in this case as T1 times T2. So note here that we have chosen to preserve the temporary name for y as well as for 2, and generated a new temporary name T3, which is going to hold that value. And then finally we have brought in x into temporary, which is T4, and then finally generated T4 minus T3 at the topmost level of the tree, or the bottommost level of the linear code. So this sequence of instructions on the right-hand side is implementing this expression by evaluating a deeper sub-expression first, which is 2 times y, and then subtracting it from x, and then keeping the value in temporary T5 at this particular point. And depending on where this expression is being used, maybe it is a part of an assignment statement. So T5 further down will get assigned to a left-hand side variable, etc., etc. And for a simple program, which I will just show here, the temporaries that get generated from it look like on the right-hand side. You can easily see here that first we evaluate, and I'll let you go through this offline, and we'll stop in a minute. First C1 is equal to 0 is evaluated. If that branch is true, then we are going to get into label 1. That basically means that we are going to evaluate this while loop over there in that label. And for that purpose, go to the label 1, lab1 colon. And in that, you can see that first we evaluate if C is greater than or equal to 0. If this statement is true, then the while loop is broken, because this negation of this condition is true, and that means the while will terminate. If it is not true, however, it will fall through, and it will do C is equal to C plus 2, and then execute continuously the while loop by visiting its top level at lab 1. So that's lab 1 till go to lab 1 is the while loop that is being implemented. And then the other side of the if statement, which is the else part of it, executes in a fall through manner at the top. You can see that first we'll evaluate n times n into T2, and then C will get evaluated here as T2 plus 2. And then obviously we don't want to go and execute the while loop in this case. We want to bypass it, and that's why we'll carry out this particular jump to go to end. And it's looks a little convoluted in terms of the control flow that is organized here, but this is pretty much how it looks if you animate it. And the code generator behind this would have made these decisions in terms of how to lay out the code and how to put these branches and how to wire them and so on to generate this type of intermediate representation. And the details of which, of course, we'll see in the next lecture, but you can trace the control flow here. That first, the if condition is checked. If it is true, go to the while loop in lab 1, continuously execute it. If the while condition is false, branch out to end. Otherwise, keep looping through lab 1. And of course, if the if condition is not true, then fall through and execute the else side of if, and then branch out to the end, shown by this go to end. So this is how these instructions which are supported in the IR will be generated from the while loop. We will talk about the details of how to go about it next time. Sorry about the snafu. Hopefully it doesn't happen again. I don't know, my network or the computer or both had some issues, but looks like we were able to get past it. Thank you, and we'll now go for office hours, and you can ask me questions there if you have any.